Okay, so how can I actually show that the all CF problem is undecidable? To do this, I'm going to mapping reduce the not halting problem to the all CF problem. Okay, because the not halting problem is undecidable, then so will the all CF problem. And so to do this, I'm going to give you the setup that I've been giving for all previous mapping reductions when I give the two steps that I need to do, right? So the two steps I need to do in this mapping reduction, like every other mapping reduction we've seen, is the first thing to convert an arbitrary instance of the not halting problem. So that's mx binary encoded as a string, because we're dealing with strings in this course, to a particular instance of the all CF problem. And so what's a particular instance of the all CF problem? Well, it's a grammar which has been created, right? The production rules of the grammar have been created as a function of mx for some specific purpose, and that purpose is in step 2. But before we get to step 2, of course, the instance of the all CF problem isn't really G, it's G, but encoded as a binary string as well. Right. So this notation here just refers to the fact that I am binary encoding G. Okay. So I need to do this, and I need to do this while keeping in mind my objective. My objective is step 2, and this objective is to show that a yes answer to this instance of the not halting problem corresponds to a yes answer to this instance of the all CF problem, and the same thing for the no answers, right? But if you translate what a yes and what a yes answer is for both of these instances, that just means that M loops on X if and only if, and the if and only if is what allows or forces this yes to yes, no to no correspondence. So M loops on X if and only if the language generated by G is equal to sigma star, where we're saying that sigma star here, remember from the previous video, sigma is the set of terminals of G. Okay? And so if you look at this reduction, it's not so obvious what you're supposed to do, right? Because none of the tricks that we used so far have really dealt with mapping reducing a problem about Turing machines and their input strings to a problem about context-free grammars and context-free languages. So this is why actually what Prakash would say is the beginning of the difficult mapping reductions. And I tend to agree with him about that. And I think so will the students who are actually at today's lecture. Okay, so this is the beginning of the slightly more difficult mapping reductions, because now we have to do a bit more gymnastics to make, in this case, a context-free grammar G, which when the all CF solver says yes, means that M was looping on X, and when the all CF solver said no, meant that M was not looping on X. In other words, it halted on X. Okay, and so the question is, well, what could G possibly be? What could G possibly be? Okay. Well, I'll give you the high-level idea. The high-level idea is that if you're given a Turing machine M and some input string X, if M is running on X, then you can study the history of computation of M run on X. Okay, so the history of computation, that's every instantaneous configuration, right? Every configuration M has during its computation on X, right? So if you create a grammar, right? If you create a grammar which, given some Turing machine M and some input string X, some arbitrary Turing machine M and some input string X, is able to kind of generate the computation history, we're going to see that that's not quite possible. So that's what I'm saying, kind of. So if you can create a grammar which kind of generates the computation history, okay, then if the computation history can be generated in a finite number of steps, right, then that means that M halted on X because there was a finite number of configuration that M visited before halting on X. But if M loops on X, that means that M visits configurations over and over again, right? So if you're writing down what each of the configurations M visited when running on X, then that string, that sequence of configurations will be infinitely long. And so in that case, there's no way for the grammar G to generate a string like that. So in that case, the grammar is not going to be able to generate any strings. And so while you're probably thinking, how does that relate back to L of G equaling to sigma star? You'll see that in a second, but it has to do with the complement. So that's the high level idea. I don't really expect you to get much of that. I need to sort of formally define what I mean by computation history and how a grammar could actually generate such a thing. Okay, so at a high level, what I'll just say is that it's related to the computation history. So it being the construction of G given MX. So it's related to the computation history of a Turing machine M running on input X. Okay. And so the intuition here that we're going to use again in a second is that if M loops on X, so if M loops on X, then there is no finite string. There's no finite string which can represent its computation. Represent its computation history, I might add. So at this point, I'm sure you're very confused. Probably you're asking yourself, what is computation history? Let me define that formally so it becomes much clearer. Okay, so a valid computation history is defined in the following manner. So suppose we are given a Turing machine M. And now, I think at this point, this is quite important to mention. Remember, the way I formally defined a Turing machine during lecture 18 is as, I think it was a 9-tuple. I'm not going to rewrite the whole 9-tuple, but remember 2 elements in that 9-tuple were the tape alphabet, so all of the letters that are allowed to be on the tape, and the input alphabet. The input alphabet was all of the letters that are allowed to be in the input string, so the string that you start with. Okay, and so we had said that, of course, the input alphabet was a subset of the tape alphabet, which made sense, right? Because, for instance, we didn't allow the dash and the blank to be in the input alphabet. Okay, so this is going to become pretty important when I formally define some other things in the next videos. Okay, but this is just something to remember. Remember that you have a tape alphabet, which is the alphabet containing all the letters that are valid to be placed on the tape. And then you have the input alphabet, which are all of the letters which can be in the input string, the initial input string that you then place on the tape. So of course, sigma has to be a subset of gamma. Okay, so we're given a Turing machine M and an input string X in sigma star. Okay, so not to be confused with the sigma I was using when I was talking about the set of terminals of the context-free grammar G. Okay. So we have this string, which is an input string in sigma star. And so then a valid computation history, history is a string, so it's a string itself, which makes sense because a valid computation history is really just a sequence of instantaneous configurations, and instantaneous configurations are strings. So is a string of the form this is going to be the form of a valid computation history. So this is a string, okay? The first letter of the string is a hash. Then it's the first instantaneous configuration, which I'm going to represent with alpha 0. Then it's another hash, right? So the hash is kind of like the separator token. Then it's another instantaneous configuration, alpha 1. And so on, right? And so on. This keeps on going. You keep on appending instantaneous configurations until you get to the last one, until you get to the hash, then alpha n, and the hash, right? And so the idea is that this is the form of the string which represents a valid computation history, but of course it has to follow some constraints, right? It has to follow some constraints, the string to actually be a valid computation history. So the first one is that this hash, like I said, I talked about this verbally, but written down, the hash is a special separator token, which is not in gamma, right? And it makes sense that it's not in gamma because I just want the hash to be there to separate different instantaneous configurations. So I don't want a hash here because then it's confusing. That means that I'm not quite sure if it's the start of a new IC or if it's just part of the instantaneous configuration. So I said IC for instantaneous configuration, right? The other thing is, like I was saying, every alpha I is an instantaneous configuration. So every alpha I is a string, right? It's a string, and in fact, the string is defined over delta star, right? Where delta is the union of two things. It's the union of the tape alphabet and the set of states of the Turing machine. The set of states of the Turing machine. Because remember, in the tuple definition of a Turing machine, you also have the set of states. Now, one thing that was confusing students is, well, what do you mean that Q is part of some alphabet? Q is just states. Well, in this case, what we're doing, we're slightly overloading notation, as is custom in computer science notation, where we're saying that Q, yes, is a set of states, but in this context, in this particular context, you interpret, say, the state Q0 as the letter Q0. Okay? And so then the alpha i's are strings over the alphabet gamma union Q, which makes sense because if you remember during lecture 18, where we were talking about instantaneous configurations of Turing machines, we had something that looked like, some tape letters, then Q, which is really acting as the pointer, so maybe Q7, and then some other tape letters, right? And so this is kind of saying formally what a string of this form would look like, okay? Not quite, right? Not quite. We'll get to that in the third condition, but close enough, right? And, well, no, actually, we'll get to that in this condition, where we say that, yes, alpha is a string over delta, and alpha I is an instantaneous configuration, right? So it has to respect the rules of instantaneous configurations of Turing machines. Okay, so that's the second rule. The third rule of this string, of this whole string, right? We're defining what the rules are for this string to be a valid computation history. These are the first two. The third one says that, well, alpha 0 and alpha n, those two alphas have a special form, right? Alpha 0 has to be the starting instantaneous configuration. So it must look like the dash, the start state S, the input string X, and the blank, right? So this is the start state It's the start state of M. Okay. But remember what we're doing here is we're interpreting states as symbols, as letters. So that's the restriction on alpha naught. The restriction on alpha n is that it's either a accepting or rejecting instantaneous configuration. So either it looks like the dash, some string, the accept state, some other string, and then a blank, or it looks like the dash, some string, the reject state, some other string, and a blank, right? And so U and V would be in gamma star. Okay, so that's the third condition. And the last condition is hopefully also logical. So right now we're just saying what each of these alpha i's should look like. But remember, we're talking about the valid computation of a Turing machine running on X. And so if you want this to make any sense, the relation between alpha 1 and alpha 0 should be that in one step of the Turing machine, you can get from the configuration alpha 0 to the configuration alpha 1. And this is what this fourth rule is going to say. So this fourth rule is going to say that for every I in 0 to n minus 1, the pairs of alphas, alpha I plus 1, they must follow alpha I in one step of the instantaneous configuration relation that we defined for Turing machines gives you alpha I plus 1, right? So this is just saying that if, in case you've forgotten this notation, this is just saying that in one step of following the rules of the transition function of Turing machine, you can move from this instantaneous configuration to this one. And so hopefully this is intuitive. Hopefully this makes sense as a definition for what a valid computation history should be. In the next video, I'll give an example of this, and then I'll talk about the set valcomps, which is the set of valid computation histories, because in this case, we're just talking about a particular string, but what we're going to be interested in is the language containing all the strings of valid computation histories for a Turing machine M and an input string X.